So we talked about queries in the last video, right? And, if we've got a DAG that looks something like this, right? We've got questions about the effect of X on Y, or how X has an effect on Y, or whatever our query might be, how those are really questions about the values of the thetas or of the lambdas, right? And we're going to use, so those are not directly observable, right? But we're going to use data on X, M, or Y, and or Y to learn about the thetas and the lambdas. So how are we going to do that?
Okay, so the approach we're going to use to figure out what are plausible values of the thetas and lambdas is the Bayesian approach, okay? And the Bayesian approach is using Bayes' rule to put probabilities on different possible values of theta or lambda that are reasonable things to believe given the data, right? And the idea is if you start off with some beliefs about how things might be, and then you see data, that data should make you rethink which values of these are most likely. So I'm going to work through, we'll work through an example here. So I ask you a very simple question. I say, look, I've rolled a dice, okay? 1, 2, 3, 4, 5, or 6. What's the chances I rolled a 6?
1 in 6.
1 in 6. 1 in 6. Here are the 6 possibilities. One of those, all equally likely. That's great. Then I say to you, what if I were to tell you that, in fact, I rolled an even number? Right. Then what's the probability?
Well, there are only 3 even numbers here, so one of them is 6, so 1 in 3.
1 in 3. That's the idea. So all you're doing with Bayes' rule is you're starting off with a set of beliefs what might be possible. You're seeing what is consistent or what's more consistent with the data you have, and then you shift your beliefs in the direction of those possibilities that are more or less consistent. And that's how it works with dice. And in our world, where we're looking at these thetas and lambdas, it sort of seems like it might be more complicated, but it's basically the same kind of logic.
Basic idea.
Let's have a look at it.
All right, so back to our really simple DAG, X and Y, with theta Y pointing into Y. And say we have a question about what the effect of X on Y is, which is, again, a question about the value of theta Y. Well, we can make some observations here. We can observe the value of X and the value of Y. So let's have a look at what some of those observations might look like and how that might map onto different beliefs we might have.
Right. So in this table here, we're imagining there's 4 different patterns you might see for X and Y. Right? It might be that X is 0 and Y is 0, X is 0, Y is 1, and so on. And then on the next 4 columns, we're saying which possible causal relations are consistent with that data. So which possible values of theta are consistent with that data. Right? So for the first case, with X is 0 and Y is 0, we see that's consistent with 2 possibilities, the positive effect, right? Or the possibility that Y is always 0 no matter what. Right? Those are 2 things that are possible. That's fine. The key thing is there are 2 things that are not possible, right? So for this case, we're ruling out 2 possibilities. There's not a negative effect.
And that's because if there were a negative effect, we'd have to have like X being 0 and Y 1, or X 1 and Y 0, right?
Right.
So, and yeah,
that's right.
That's ruled out by X
exactly.
and Y both being 0. Yeah.
Exactly.
Yeah.
So you see across the 4 different types, you're always actually ruling out 2 possibilities, right? And allowing for 2 possibilities. So at the case level, if you start off with very flat beliefs about what's possible, you update a bit, but there's a lot of uncertainty still remaining. How about at the population level?
Yeah, well, let's imagine, so instead of thinking of one case where we might see each of these 4 values, let's imagine we look at a few cases, right? And here's what we see, right? We see 2 cases, the first 2 rows, in which X is 0 and Y is 0. And we see 2 more cases in which the 3rd and 4th row, in which X is 1 and Y is 1. So are we going to learn from that? Are we going to update our beliefs from that?
So here, if we're interested now in the question of what is the distribution of thetas in the population, right? What is lambda, what we're calling lambda Y, right? We can see, well, if it was all of the cases are consistent with the possibility that there's a positive effect, right? They're all consistent with that. All 4 of them are consistent with that. None of them are consistent with the possibility there's a negative effect, right? Now, that's not to say there might be a negative effect for some share of cases, but certainly for the data we've seen, there's no evidence for a negative effect, and all the evidence pointing away from negative effect. And 2 of the cases are consistent with there being a lot of cases for which Y is always 0, and 2 are consistent with there being a lot of cases for which Y is always 1. right? So with this particular combination we have here, we're seeing there's some distributions of types for which this would be quite likely, and some distributions of types for which this is going to be very unlikely. Right?
And so, like, one can imagine, like, we go in perhaps with uninformative priors, like flat priors where we think each of the 4 types are equally common in the population. We see these 4 cases, that's only 4 cases, but we're going to shift at least a little bit toward a belief that positive effects are somewhat more likely, negative effects somewhat less likely.
Yeah, and some things we rule out. We rule out the possibility that there are negative effects everywhere, right? So there's some things already that are ruled out, although mostly we're just shifting, as you said, in some ways or the other.
And with more data, we're going to shift more strongly. If with more data of a similar pattern, we're going to shift more likely in that direction.
Yeah. Let's look at the next set of slides, which is interesting in 2 ways. This is different to the last one, partly because it could be consistent with a more complex DAG. It's a DAG that's got 3 variables. It might be one in which the chain DAG, like we saw, X causes M causes Y, perhaps, or the 2-path, the 2 different possibilities. That's one way that's different. The other way it's different is that we have data on X and Y for all cases, but we don't have data on M for all cases.
Right. So this in sort of small form, we might think of as analogous to a common sort of mixed method research design, right? Where we collect data on a few causal variables and an outcome variable for a whole set of cases. And then we go deep and collect, say, process data on a small subset of those cases, right? So we've got a data structure that kind of looks like this.
Exactly. And we've sort of set this up deliberately to make another point, which is, if you just look at the XY relations here, you'd say, oh, it looks here like there's a pretty strong relationship between the X and Y. If you had a chain model, like so X causes M, M causes Y, that's how it goes. You should then be thinking, so it must be that X is having an effect on M and M is having an effect on Y. But if you look even at the small number of cases you have here with M data, you see, well, that's the M relationship is kind of inconsistent with X causing M.
Right. To say they're not correlated here.
Not correlated here.
Yeah. And of course, we're showing this with a very small number of cases. And with a very small number of cases, you're only going to update a little bit. But the analogy here is to imagine a larger data pattern to look like this. And you would learn a lot from those M observations, potentially, even if you don't have them for all cases.
Yeah. And even if you don't know ex ante, should X have a positive effect on M or should X have a negative effect? You might be uncertain about exactly how X relates to M, but believe it must work through M. And this is already enough from the process data to start questioning some of what you might have got from the overall pattern.
So, back to, this is our inequality and democratization DAG you'll see a lot of in the book and talked about in an earlier video. The idea is that we're going to collect data. That data could have sort of really any imaginable structure to it in terms of which nodes we have data on from which cases. We're going to ask this question, basically, what sets of beliefs about lambda, about the proportions of different kinds of nodal types in the population are more or less consistent with the data pattern we're seeing. We're going to update our beliefs, based on the data, using Bayes' rule. Now we've got this updated model. We also know how we can take the questions we have about the world, and map those on to our thetas and our lambdas, So now we can put really any causal question that's defined, sort of can be specified. We can put those questions to the updated model.
I'm just going to repeat that because that's just the heart of it. Yeah. What we showed in the last slide was you take any question, once you have this model, that question is a statement about the theories and lambdas. In this talk, we've shown how with the data you can update on the thetas and lambdas, but that means that you have all you need to update on the queries themselves, which are statements about the thetas and lambdas.
And I'm just going to underline one part of that, which is that I think in a lot of approaches to inference, we think about, I have this question, Now I'm gonna figure out what kind of model I need to estimate to answer that question, right? And now I have a somewhat different question about the same sort of phenomenon. I need to estimate, a different model. Here, we update the model with the data. In a sense, it's update once, and then you can query that updated model. You can ask it as many questions as you like. And we can sort of think of there being a couple of different ways in which this, sort of modes of inference we might be in here. One is we might have questions about the population, right? So we see data, we update our beliefs about lambdas, that is our beliefs about what share of the population has what kinds of effects at each point along the DAG. And we use those updated beliefs to answer population level questions like what's the average effect of inequality on democratization, or how much of the effect runs through it.
Those can all be read directly from the lambdas. What we believe about the lambdas, calculate those out.
Exactly. But then there's another way we can think about this, right? As a way of strengthening qualitative inference or process tracing, right, on cases, right? Because we get into this in the book. One thing that we're learning as we're learning about the lambdas is potentially we're learning about the probative value of observations that we might make within cases. So for instance, if we're looking at a case that democratized and we see that there was mass mobilization, what does that tell us, if anything, about whether inequality caused democratization? Well, instead of just sort of positing that M had some probative value here, our updated model could tell us what kind of probative value M has. In other words, so that when we go in to a specific case and observe mass mobilization, the inference we draw from that is actually undergirded by the updated model, i.e. it's informed by the large N data.
Right. So for example, if we were really convinced from the large N data that the link between I and D runs through M, that I causes M and M causes D, then we really should expect to see mobilization, whatever inequality causes democratization. So if we don't see mobilization in a particular case, then we lose confidence that in that case, the inequality that existed caused the democratization we see. That's actually an instance of a hoop test.
That's right. And so the inferences here are integrated, in a number of senses, right? We're mixing data strategies, but we're also using, in a sense, one method or one sort of data strategy to strengthen our use of another mode of inference, right? The process tracing. All right, let's leave things there.
Yeah.